Okay, so I'm going to tell you about a new technique which we have been applying over the past few years to study the formation of edge modes and surface green functions, starting from impurity-induced states. And we've been doing this using exact solutions via the T-matrix approach. This work has been done in collaboration with my ex-student who was a postdoc at that point, and with my other ex-student who now, well, not working in physics anymore. Okay, so what's the story behind this? So what we do, we start, for example, let's take a 1D wire and we add an impurity. When we add the impurity, we form bound states around the impurity. Now imagine that this impurity is very large, that it goes to infinity. Then intuitively, then at that point, the wire is going to be disconnected into two semi-infinite pieces. So we expect that the bound states associated with the impurity are going to actually become edge states or end states when the impurity is going to infinity. So that's the intuition behind this, this approach. So if I'm in one dimension, like I said, I'm adding an impurity, and when my impurity goes to infinity, I'm forming end state. So if I have end state of a wire, if I'm in 2D, I can do the same thing with adding a one-dimensional line impurity. And when I take the potential of this impurity to infinity, what's going to happen is that the bound states associated with this impurity are going to be edge states, what we know as edge states of two-dimensional system. Okay, so the general procedure is take any infinite system. It can be 1D, 2D, or 3D. Then introduce either point like, line like, play like scalar impurity described by a delta function potential. Then use the T-matrix formalism to find the energies and the wave functions associated with the impurity bound states, and then formally set the impurity potential to infinity to recover the formation of boundary modes. So this is a general prescription which works in all dimensions, and it gives us either end states, like edge states, or what's sometimes more interesting, surface states, because surface states are numerically much harder to obtain otherwise. So I'm just going to spend one slide on a bit more technical details. I mean, I'm not going to be very technical after, but I'm just going to give you the, the mathematical background of this. We know that for an infinite system, this is the general Green's function, is the unperturbed bulk Green's function. We use the retarded Green's function. Then I'm adding to the bulk, to the infinite bulk, I'm adding an impurity, and this is the Hamiltonian of the impurity potential of the impurity. So I know that if my impurity is a delta function, so it is localized in space, then it's going to be independent of momentum when I take a Fourier transform in momentum space. And this is what saves me, and that's why I can solve this problem exactly, because this independence of K allows me to find the exact Green functions of the perturbed system. And the method to obtain this Green's function, the perturbed Green's function of the system with an impurity, is called the T-matrix, and it's just a sum, like a perturbative sum to all orders in the impurity potential. So my perturbed Green's function is going to be the zeroth order Green's function plus all the terms coming from scattering. So I take the one impurity, the scattering once by the impurity, then scattering twice by the impurity, and then scattering to all other orders in perturbation theory. And normally the sum cannot be done exactly, but like I said, if the impurity is localized, if I have a delta function potential, then I can sum this. Exactly, and I can obtain an equation for the T-matrix, which is going to have an exact answer. So then also my Green's function is going to be the perturbed Green's function for the system with one impurity is going to be exact. So I make absolutely no approximation. This whole procedure is fully exact, and I'm getting the exact full Green's function for a system which has a boundary. So, and I can, actually, it's even deeper than obtaining the end modes or the edge modes, end or edge modes, because it's actually telling me all the information about the semi-infinite system. I mean, I can get the Green's function not only on the edge, but at all other positions in my semi-infinite system. And if I apply it twice, because I can apply it twice in a row, I can get the Green's function of a fully finite system, like of a ribbon, for example, or of a finite size wire, or, a finite size slab. So because it can be applied twice in a row, once for the first edge and second for the second edge. Okay, so now I'm going to give you some examples of where we apply this. So we started with the basics and then we kind of went up to whatever we could think of. I mean, it's going to, in this talk, it's basically going to just go, I'm just going to go through some of the classic examples, some of which you are probably familiar with. I'm going to tell you how this method actually works. So graphene, we all probably know about graphene, hexagonal lattice, 2 atoms per unit cell, hopping terms between the nearest neighbors, some Hamiltonian, which comes out of this hopping terms, some energy dispersion associated with. Then I have a band structure, and we know that the band structure of graphene is composed of 2 bands, which touch the 6 corners of the Brillouin zone, and around which I have some linearly dispersing quasi-particles. And what is interesting about graphene, I mean, maybe not so interesting, but is one kind of funny thing happening, is that if I cut it, if I take, if I have an edge, for example, a zigzag edge, because armchair is not as nice for graphene, then it's going to give me some funny states localized on the edge. So the classical way to see these things is numerical. I'm just going to make a ribbon out of graphene, and then I'm going to look at the band structure of this ribbon and how I'm going to guess the band structure of this ribbon, if there are not the edge states. I mean, I'm taking the bulk band structure of my system, it could be graphene or something else, and then I cut it by the allowed vectors, the allowed wave vectors that are given by the quantization along the y direction here. So if I were to have a ribbon, then I have a finite size in the y direction. So then I have some quantization of the mode in the y direction, because I can no longer have all allowed values of y, because my system is finite in the y direction. So then it means this band structure is no longer valid, but I have to project it along lines which are given by ky, which is 2 pi over the size of my ribbon. So I draw this a bit schematically here, these lines, and then I have to cut this band structure along these lines and project it like that. Then I'm seeing that I have all these lines, all these band structure lines, which are going to be the band structure, which are going to make up the band structure of my ribbon. And if you look carefully at this band structure and the allowed wave vectors in y direction, then you're going to see these these black lines. And but there is another thing when you do numerics. Besides the black lines, you get an extra line, which is the blue one. The blue one doesn't come from the bulk. There is no line which is flat. There is no band which is flat in the bulk band structure. So this blue line comes from the edges. So this blue line comes because I have an edge. If I did not have an edge, I didn't have this flat band at 0 energy. So this is extra, and this appears in the numerical simulation, that this extra energy band, which is localized along the edge. And I want to recover this using our technique. So what we do then, we take graphene, we write again the bulk Green's function. Then I'm taking a line impurity here, which is localized along these blue atoms. And you see that when I do that, I'm going to cut my system into 2. But if you look carefully, on the left, I have a zigzag edge. And on the right, I have something which is called a bearded edge. I mean, they're a bit different. If I were to recover zigzag edge states on both sides, then I would have to take 2 lines of atoms. I mean, we did that also, but I mean, in this example that I show here, we only took 1 line of atoms. The blue one. So then I have 2 types of edge states in my system, and together these 2 types of edge states are going to give me 3 segments of zero energy states, and one of them, the one in the middle, this one, comes from the zigzag one, and the latter one come from the bearded edge states. So it means that I recover using my technique this flat 0 energy band, which is localized along the zigzag edge. So my technique is actually recovering perfectly the band structure of graphene. And this is a semi-infinite ribbon, but like I said, I could put two edges, and then I can recover the finite size ribbon also. Okay, so now the second application, which is more topological. So graphene was kind of a standard classical system we wanted to start with, but then the second system that we wanted to look in, which was very fashionable in the past years, is Majorana states. So topological states. These are edge states or end states, depending on the dimensionality of my system. They are like probably aware of condensed matter version of Majorana fermions, their own antiparticles. They are equal combinations of electrons and holes. They are self-adjoint. The Majorana fermions in particle physics have fermionic statistics, but the Majorana states in condensed matter have an interesting characteristic, which makes them quite, fashionable for this quantum computation discussions. They have non-abelian statistics, so that's why people are very interested in using these Majorana fermions for various applications nowadays. And their formation is topological, does not depend on the details of the system, on disorder, and so they are protected and more stable than classical qubits if I were to use them in a quantum computer. And the materials have been proposed to host Majorana states are like P-wave superconductors, though I'm kind of not sure about how P-waves these materials are for now. And much more in the past few years, the semiconducting wires with strong spin orbit coupling, Zeeman and superconducting proximity. There have been a lot of work on these wires showing that in principle they could form Majorana states, they could be topological. And the experiments that are investigating this are seeing some signatures that are consistent with Majorana, but nobody can show for now definitely these are Majorana. There are just some signs that they could be there, but there is a lot of discussion in the literature if these are actually Majorana or not. So I'm not going to say that we are seeing them because I'm not really sure about that. Personally, I don't believe, but many people think they are. Some people think they're not. But anyway, or there is another system, magnetic atom chains, or also people are claiming to realize this state. Okay, but for the purpose of my talk, I'm going to take a simpler model than the wire with Rajba spin orbit and Zeeman. I'm going to take just a spinless model, the Kitaev model, in which I have some pairing, which you see is a superconducting pairing, which is coupling nearest neighbors. It's not an on-site pairing like the usual S-wave, so it's a P-wave type of pairing, which couples like nearest neighbor atoms. If you know, people like Kitaev worked on this model, and then they showed that this model is supposed to be a P-wave and have Majorana end states. So what we want to diagonalize it numerically first, then look at the local density of states for a finite size wire. You see that you have, the bulk bands, but also you have two states forming at the ends of the wire at zero energy, and these are the Majorana states. So this is a numerical approach to this to solve this problem, an exact diagonalization, like same for the graphene. But then we can do the same using our technique. I take an impurity potential, which has this form, delta function potential. Then I'm solving the problem using the T matrix, like I said, and I'm looking at the states, the bound states, which are forming around this impurity with our technique. And here I'm plotting one example. I'm plotting the energy of this, what we call Shiba states, the impurity states in the superconducting system. And we see that the energy of the state is actually going to zero and the impurity potential is going to infinity, which is consistent with the fact that when I take this impurity to infinity, I have two semi-infinite systems, and the bound states which actually form around the impurity are Majorana states because they form a zero energy. And another test that these states are actually Majorana is that I can calculate with our technique also their wave function analytical. And this is a very nice example here because you see that I can get exact analytical wave functions for the bound states. So for the end states, and I see that the electron, the whole component of my bound states are the same in absolute value. So it means I have as much electrons as I have holes in my wave function. So this is the property of the Majorana state. So I see that the states which are forming at U going to infinity when the impurity is cutting the system into two are exactly Majorana. They're at zero energy and they have an electron, the whole part, which are equal. So my technique works also for that. So then even next step is to look at 2D at Majorana edge states. Again, this is something you've probably seen a lot. Then you have a ribbon, which can be hexagonal lattice or square lattice. You add some ingredients to the bulk of the ribbon, like some magnetic properties and some superconductivity. And then you have theories which predict that on the edges of the system, you're going to have Majorana edge states. They are the same as the Majorana end states, but they are in 2D. So that means that they propagate, they still have one momentum free momentum. And if I plot as a function of this momentum, the energy spectrum of the states, you see that they are linearly propagating and they cross at zero energy here at k equals 0. So this is a signature of a system which has a gap, and inside the gap you have these edges which form and that are propagating. If you remember graphene actually was gapless and was forming flat bands, was forming like zero energy flat bands, which are the non-topological edge states. Here I have a system which is gapped in the bulk. So this is the bulk of my system, and the edge states are actually linearly propagating. They're not flat bands, they're linearly propagating. So this is the Majorana edge states. So now my technique, before I do that, so this is the numerical simulation for a simple model, the Kitaev model in 2D now, and this is the band structure obtained with an exact diagonalization. So the numerical solution to this problem. Again, you see the bulk which is gapped, and then you see these linearly dispersing Majorana states which are crossing the 0, and these are like localized on the edges. So now I apply my technique, and I'm taking the infinite 2D system. I'm taking the line impurity. I take the line potential to I take the line impurity potential very large. Here it's 100, but it's very large compared to T, so it's infinite in the first approximation. And then I see this plot is not the best for this paper. We didn't use the best contrast possible, but anyway, you see that you form here the bulk bands and also the edge band, which is linearly dispersing, and you have them exactly the same states which are obtained using numerical simulation, obtained by our technique using again this T matrix formalism, the perturbed Green's function in the presence of the line impurity potential. So this is again an exact solution, nothing numerical. The only thing numerical that you have to do in this approach is an integral over k. But okay, you don't have to call that numerical. So the only thing you need to do is one integral over k, and all the rest is analytical. So that's quite nice if you are not a specialist in tight binding methods, exact diagonalization methods, and things like that. You can do this in 2 lines of Mathematica or something. So it's very cute because it gives you information about a lot of nice systems that you cannot approach if you're not a numerical guy. Okay, so one more example, the Kane-Melle model, model for a topological insulator. I'm not going to spend too much on it. It's also hexagonal lattice, some magnetic terms which are coupling next to nearest neighbors atoms. And because of this coupling, there have been predictions again to have some edge states here. They are not Majorana, they are just topological edge states. This is not a superconductor. Again, when you do you solve this problem using our technique, you get exactly the same thing. When U is going to infinity, you recover this propagating edge modes from the perturbed Green's function via the T matrix approach. Now, something which I find not more interesting, but maybe for a theorist who doesn't know numerics, even more useful is the 3D systems. Because okay, even I if I really spend a lot of time, I can write the code for a square matrix in like 2D and try to do an exact diagonalization of that. It's probably not going to be very nice. It's going to take a long time, but well, let's say I could do it. But 3D, then it's becoming complicated because I can have a lot of couplings between various. I could have like different atoms, different planes. Okay, 3D physics is usually quite messy. So it would be for me really hard to code like a 3D system and try to look at the surface Green's functions for that. If, for example, this system, the Weil semi-metals have a Hamiltonian which is not at all trivial, and the nice prediction about these materials that they have some surface states which people call them Fermi arc states. They're states which are localized on the surface, and they live only along an arc in K space, finite size arc, which is some sort of a banana shaped arc sort of. There've been a lot of, I'm not getting into that, interest about why this would be useful and why they are nice and blah, blah, blah. So, but for me, in terms of modeling, what I want to show is that my method actually recovers very well the state. So I'm again doing the same procedure. I'm perturbing my Green's function, and then I'm writing also a different formula for the surface Green's function. Before I was just looking at something average over the entire system. You saw that I could recover the end states and the right states, the end right states and the left states at the same time. Here I'm going to focus on a surface Green's function, because many times in this type of problem, I'm not only interested in the formation of the states, but actually what is the Green's function for the surface. Because imagine that I want to know more than if I have surface states. I want, for example, to add an extra impurity to my surface to see what are going to be the impurity states on the surface of my system. Imagine I have graphite and I have an impurity on the surface of graphite. I want to know how my bound states on the surface of graphite are going to be and how they are different, for example, the bound states in graphene, in simple graphene. So I can get more information from my problem, so I can basically get an effective Green's function for the surface. So this is going to be very helpful, because it's going to be a basis for whatever other things I want to do with it, like adding an impurity or whatever. So this is my surface Green's function is going to be like the bulk Green's function, but it's going to be localized at the position of x and x prime, which are going to be plus or minus 1 below or above the impurity plane. And of course, the K1 and the KZ are going to be free, because I'm not touching those momenta. I'm only working in the perpendicular direction to the impurity plane. And indeed, when I do it, this is one typical model for such a system. As you can see, it's quite messy, it's quite complicated, there's a lot of terms. And then when I'm actually using my technique and I'm looking at the surface Green's functions and the surface states associated with it by the spectral function, this is part of the trace of the surface Green's function, I see that I form these Fermi arcs. So depending on the model, I can have 1 Fermi arc, I can have 2 Fermi arcs. And in some even more complicated models, I have 2 Fermi arcs which are not at the same, which are a bit asymmetric, or I can have 2 Fermi arcs in some sort of a Fermi pocket in the middle. So I have a lot of, bizarre physics happening on the surface, depending on the parameters of my models. And then, well, I don't think. I know I haven't put it here. What we did was to add an impurity to this type of surfaces, and then look at the quasi-particle interference features associated with the localized impurity to predict what would happen in an experiment in which would have an impurity localized on the surface, and you'd want to look at the features associated with that. And there have been other a bit different uses for this type of method. Not only, for example, here I'm showing a system in which I'm not using my impurity to cut the system in two, but I'm using an impurity which is finite to simulate like a chain of impurities. I can simulate a chain of magnetic impurities or scalar impurities, and this is used a lot nowadays in the topological materials problems, because people look a lot at what we call Shiba chains. So we add a chain of impurities on a superconducting substrate, and then I look at the physics of this Shiba chain, and oftentimes this chain has Majorana at its ends, has some topological properties. This chain of magnetic impurities which are localized on an infinite substrate. So my method here gives me the advantage that I can also simulate the Green's function of this impurity chain, infinite impurity chain. And if I have the infinite impurity chain, I can either add an impurity to it to cut it in two and see if I form Majorana, or I can look at the chiral invariant of this effective Green's function and see if it's topological or not. So we tried all these things. We tried the chiral invariant, and we tried what happened if I were to add one impurity probe to cut it into to form Majorana. And our techniques gave us that they're all consistent, and they could predict us the phase diagram, the topological phase diagram for a Shiba chain of impurities localized on an infinite substrate. So, and this provides a lot of advantages, because when you simulate numerically this system, you have oftentimes problems because of the finite size system, because you cannot simulate. I mean, okay, you always you always have some sort of, ends, edge states associated with the big system, or you have some other, finite size effects associated to the bulk. But the advantage of the system is that it's infinite and it doesn't have any finite size problems. So it's quite nice also from this perspective. Okay, so I mean, not going to tell you much more than that, but I'm going to repeat that this is a non-numerical method to obtain edge states and surface Green's function. It's very easy to implement even for very complex systems, which provides an advantage for us who are not always numerical guys. You can generalize, if we generalize, like I said, to two impurities to get ribbons or to get even bound states in a normal superconducting normal superconducting SNS system. For Andreev bound states, we had to do some RT, to turn things around a bit, but we managed to even get the physics of Andreev bound states using this technique. We also applied it to graphite, which is quite nice, like I said, because graphite, people imagine that graphite is exactly the same as graphene. Even if you have more than one layer, then you're going to get the same thing, but it's actually not the case. Graphite, when you look at the surface of graphite, there are differences from just a simple layer of graphene. States are more localized, they decay much faster. So there is a lot of difference from simple graphene. People didn't look into that. So with some experimental groups in California, we looked at that and we saw the differences between graphite and graphene. And using our technique, we could predict it also. So like I said, surface states and edge states of complex materials and also impurity chains. So I mean, and you can imagine yourself other applications. So we are just kind of starting to explore all these things. So, okay, thank you very much.
Merci, Cristina. Are there some questions? Okay.
Can you apply this also to interacting systems?
No, for now you need a single particle Green function to do it. Maybe you could do some Hartree-Fock, but otherwise, for me, you need a single particle Green function to start with. If you can approximate that, then yes, but otherwise, no.
Okay.
It's a semantic question. A chain of localized impurities looks like a wire or just the boundary of 2D substrate. Why do you call it chain of impurities rather than just?
I think it's more like a community, experimental community discussion, because they start with some magnetic atoms added on, for example, on a surface, and they make a chain. So I think it's been probably, people have started to call it like that because they experimentally is just a chain of atoms added on top of a substrate.
Yeah, but it has nothing to do with the property of any kind of single impurity in that sense. Word impurity. No, forget about.
It's like a wire. You can imagine
just,
it's a finite size wire, but because it's made of particles that are added one by one or experimentally made to be, aligned to be one by one, it's a chain. It's not really a wire because it's not. It's like single impurities which are still, they can be still far apart. I think it can be like a few lattice spaces apart, and but it's not really a wire. It's not like a material wire. It's just a 1D wire which is made of single atoms which are spaced at some distance. It's a semantics problem.
Spaced pinned, so they don't have internal structure. They don't recognize.
No, they don't have internal structure. No.
Other questions?
So, can you also imagine impurity models where, depending on the strength of the impurity, the nature of the pinned impurity state changes? For instance, I don't know, in a Kita chain, could you imagine to have something where for a weak impurity, you have to localize Majorana states which then bind together for stronger?
Yeah, that's what happens actually. I mean, when you put a small impurity, you can imagine, I mean, the physics is the same as having two Majorana systems coupled. So basically you have two gapped Majorana which are interacting and they gap, they go to higher energy. The stronger the impurity, then the decoupled, more decoupled are the Majorana and they go to zero energy. So you can think about it in the other way. If the impurity is more, then it's like you have two coupled system, and because of that, the two things interact and gap. And then if you increase impurity, they just decouple and go to zero. Yes.
Okay. And then I have another one, if you allow me. So if you consider P-wave superconductors, we know that Majoranas can be bound also by vortices there.
Yes.
We have odd vortice.
Yes.
And in that case, could you also compute the exact wave function like?
In principle, yes, and I actually did it. I actually did numerically, but that's not, as I say, it's not our technique. It's just a T-matrix. You just add an impurity and then some sort of structure to your phase, and then you. I'm not even sure you can do it exactly because I think you need to impose some phase constraint. I know
yes,
that I did it
there is a
numerically.
phase constraint to impose it.
I'm not sure T-matrix is exact in that limit. I know that I did it numerically. I could recover the vortices using tide binding, but I haven't tried analytically. I mean, it's also it's something more classical. It's just a single impurity problem. It's not our our problem is more like to manage to use this impurity to separate two systems into two. The having a vortex would be just a single impurity problem. So I think many people look into that before using more classical techniques.
Okay, thank you.
I have a question, but I don't know, is it meaningful or of interest to try to look what's happening in 2D, say, when you have a curved interface? And could you try to extend your...
You mean you have something which is not straight, it's not a straight line?
Yeah.
Yeah, it's meaningful because there are a lot of interesting physical systems in which the boundary is not straight. For example, you have this high order topological insulators, you have, bound states with forming corners. So there, our technique doesn't work because you really need translational invariance in one direction and then a single impurity in the other direction. So we tried, but you can do some sort of another variation of this method, which is a bit more, it takes a bit more time, is that what you do, you take an infinite system and then you add, you make your boundary point by point. You put one impurity, then the second one, so then you generate whatever curved surface you want point by point. So it takes a bit more time because you have to apply T-matrix each time at each impurity, localized impurity, but you can make whatever boundary you want in 2D. And you still get the full Green's function for that. It just, well, you have to do a code in which you apply this method like 100 times or whatever many times you want to generate your boundary.
Okay. Okay. So let's thank Cristina again.